Okay. So now we will start our lecture. I welcome you all in this lecture. I'm glad that you have joined, taking time to face me, to bear me. So I'm here once again to bore you uh, in the topic surface tension. Okay. So this is the way of interaction. I'm not really going to bore you. I think you enjoy with me because I enjoy a lot with you. Okay. Now, okay. So now let's back to the story. So we have a story of fluid mechanics. We have completed that, and now we are dealing with the surface tension. We have covered a lecture. No, we have already done a lecture. This is lecture number 2. In the previous lecture, we have seen what is the cohesive force, what is the adhesive forces, what is the functioning of that, the real life examples of surface tension, and what is the concept of surface tension. That all we have discussed. Although we have also discussed the surface energy associated with it. Okay. So now we are going to deal the rest of it. So today we are going to do the excess pressure inside the liquid drop, air bubble and soap bubble. Okay. And then angle of contact in capillarity. So these two topics we have to cover today. And this is it. So are you ready, guys? Because I am super ready and ever ready. So we have talked about the adhesive forces and cohesive forces. We have talked about the surface tension. It is nothing but the force, or you can say the force here is nothing but surface tension per unit length, or you can say force per unit length. Just a second. So the force acting per unit length is considered to be a surface tension. Got it? Now, what is adhesive forces? Adhesive forces are those forces which act between different molecules, and it is a kind of intermolecular forces of attraction. Cohesive forces are those forces which act between the same kind of molecules. Okay, so that forces will be, although it is also a intermolecular forces of attraction, but acting between the same molecules. Now, I think you guys have revised the concept. So today we are going to do the excess pressure inside a liquid drop, air bubble and soap bubble. Although we have covered some of the stories of it, but we will see it from the beginning. Okay, got it. So what is excess pressure? Look, there is a liquid drop. There is a liquid drop, let's say. So we know the property of surface tension and we have discussed it. Ki surface tension, due to the surface tension, any kind of material or liquid or fluid on which this surface tension can act, this surface tension tends to achieve a minimum surface area. Minimum surface area. So due to this property, this surface tension want to collapse any kind of particle or any kind of drop we have. Okay. Now, because of that, the pressure outside the bubble and inside the bubble will be different. Because if anything, you want to collapse it and it is not collapsing because rain is falling, we have drops, we have air bubble inside a liquid. So these are forming now. Okay, that is why we are discussing it. So if surface tension want to collapse it, so there must be a counter of it inside because it is not collapsing. It has a particular shape. Okay, for some time, let's say, because after some time it will just collapse. Okay, but meanwhile, in that time, this surface tension must have a counter. If it is surface tension, so it must have a counter in the opposite direction. Got it? And that counter is termed as the pressure inside the bubble or air drop. Okay. So that is why if outside pressure is, let's say, PO, inside pressure is, let's say, PI. So this PI is greater than this PO. Got it? And if this is greater, PI is greater than PO, so there must be a difference of that. It exists and it has a finite value, positive value. So this value, difference of pressure inside the bubble and outside the bubble, is termed as the excess pressure, extra pressure that we have. Okay. Because if the pressure would be same, the bubble will not form. Okay. So due to the property of the surface tension, a drop or a bubble tries to contract. Got it? So it compresses the matter enclosed in it, and thus in turns increase the internal pressure. This pressure is termed as the excess pressure. Got it? I think this is clear now. Now, this is the air inside the balloon, and this is the air bubble. It is nothing but, you have seen it in the practical life also. When you pour the liquid in any glass, you will see there's a bubble coming out of. Okay. So these bubbles are the nothing but the air bubble inside the inside that particular container. Okay. And these you must have known, because all of you have played with this in your childhood. Okay. So this balloon has air inside which constantly pushing it out, and the air outside the balloon is try to compress it, but it is not compressing it. So inside pressure is greater than the outside pressure, and this is termed as excess pressure. Now we will see the excess pressure inside a liquid drop and air bubble. Because liquid drop and air bubble are same, let me tell you the story behind it. Let's say this is the liquid drop, this is the liquid drop, and this is the air bubble. So who can, any one of you can make the air bubble? Just give me a thumbs up if any one of you are able to make air bubble. This is air bubble. So air bubble, the concept of air bubble is valid only inside a liquid, because if this is the liquid and this is the air bubble, this can be possible. This is air and this is water, so air is applying pressure to this, but at outside this is only air. So how can we form an air bubble? It is not possible. It is only possible when it is inside the liquid. And the expression for air bubble and liquid drop is same, because in liquid drop inside there is liquid only. So this free surface, the concept of free surface, which is exposed to the atmosphere or the contact surfaces. So how many contact surface we have? If you just cut it, okay, if you just cut it, you will have a shape like this, and this is also filled with liquid. Okay, so inside this surface you have only liquid, and at this surface you have air, and inside liquid. So there is only one surface which is interacting with liquid air, and inside there is only liquid. So free surface, there is only one free surface in that case, because inside there is water or any liquid, and outside if you will see, It can be air if it is a raindrop. Okay. Same thing with this air. Inside there is air only and outside the liquid. So surface will change its property from here at the surface. So only one free surface we have. Okay. Only one free surface. The interacting surface is only one. Got it? The interacting surface is only one, which is liquid and air. Got it? And same in this, it is liquid and air. So that is why the expression for both the liquid drop and air bubble is same. But if you talk about the soap bubble, we have also make it with the soap bubble blower that comes. It's a very famous toys in the children's. So if you talk about this soap bubble, so soap bubble is made of a very thin liquid film. This is a liquid surface. Okay. So here you can say inside there is air only. Okay. And outside is also air. So how many interacting surfaces are there? Air and liquid. This is the first interaction. And outside air and this outside film will have the second interaction. So here we will have two surfaces of interaction. So in soap bubble, two free surfaces we have over the contact surfaces. Okay. Now you are clear with this. It will help you to understand the concept, the expression, how it comes. Let's say this internal pressure, because it is greater in value, so it will try to expand the bubble. Okay. And in expanding the bubble, we have to done some work. Got it? And that work done is somehow related to the surface energy, because work done is kahin na kahin work done is associated with the energy. Okay. So let's say the radius of this liquid drop is smaller and internal pressure is Pi. Outer pressure is Po, and it has extend the radius by a very fine value of dr, and there is a work done in doing this process. Although what we are doing, we are increasing the volume of it. Only if radius will increase, the volume also will increase. The bubble will become more bigger in size, so the volume is increasing, and we know that work done is nothing but P delta V. Okay. Now excess pressure is Pi minus Po. So at equilibrium condition, what will happen? The work done by the excess pressure inside the liquid or inside the drop will convert it into the surface energy of that particular drop. Okay, because if you are increasing the surface energy will also increase. Na? If you increase the radius, the surface will increase. The surface will increase, hence increase in the surface energy. So whatever the work we have done will stored in the increase in the surface energy of the liquid drop. Now, what is the work done? So work done, I have told you, it is P into delta V. Delta V will given by area into length, which is the this value, this much. Only this strip. Okay. So we have area A and length R. Okay. Length dr. So volume, we will say that it is area into dr. Got it? So that is why area, surface area is given by 4 pi r square dot dr. Pressure is P. The surface energy, we know that it is surface tension per unit area, change in area. So here we have take surface energy, surface tension into delta A, because we know that surface energy is equals to surface energy divided by area. Surface energy per unit area give you surface tension. Okay. So from here you can say that surface energy equals to surface tension multiply with area. So change in area we can also calculate, because now the area, the radius will become r plus delta r. So area will be, final area what will become? It will become 4 pi r plus delta r square. Okay, that is we are going to do here. So any point of time, if you have any kind of doubt, you can ask immediately that. Okay, so delta is the area final minus area initial. In final area we have r plus dr minus 4 pi square. So we will open this expression. It will become like this. The formula of a plus b whole square, a square plus b square plus 2ab. Now this dr is very small and you are doing the square of it, so it will become very very small then. So we can neglect this dr square. So we will only consider this value, 4 pi dr square 8 pi r dr. We can consider this dr square is very less, so we will remove it. We can neglect it. So the final expression, the final change in area we will have as 8 pi r dr. So from this equation, P into 4 pi r square dr equals to S into 8 pi r dr. So there is a war and they will cut each other with the swords, katana and all. And finally, we will left with these values. Okay. So P here equals to 2s upon r. This is the formula that you have to remember for excess pressure inside the air bubble and liquid drop. Got it? Now, you can also skip the expression for soap bubble and directly make the conclusion here. Because the soap bubble has two surfaces of interaction, so the surface energy will increase 2 times for each surface. So we can also say that this change in surface energy will be 2 times of it. It will be 2 times. So this expression will become 4s upon small r. This is for the soap bubble. Soap bubble. So you do not need to look at the expression. All the things are same, just you have to multiply with 2. And why you have to multiply with 2? Because it has two surfaces of interaction. One is with liquid air, outside air, and one is inside air and liquid. No. I have told you all the things. The same thing, only we have to multiply it with 2 due to the two surface inside and outside. Now you have 4s upon r. This is the expression for it. Okay, so this is the excess pressure inside a soap bubble. Got it? And one thing I will also tell you, that if this is a container and there is a liquid fill inside it and there is a bubble of air inside it, it will also termed as the cavity. We can also say the cavity. Okay. Now ready for a challenge? Yeah. So what happens when two soap bubble, okay, collapse together, and what will be the common radius after collapse? We have seen it when two soap bubble, one is smaller radius, one is bigger radius, come closer, they will form a bigger radius pair. Okay, so we will see the expression of it and how it will be there. Now we know that because soap bubble ke liye excess pressure is 4s upon r, so P is directly proportional to 1 by r, which means as the radius increases, the pressure will decrease. So student of JNV Ramnagar is saying it is R1 plus R2 by 2. Okay, let's have a look whether it is correct or not. So from here you can say that this excess pressure is inversely proportional to the radius, which means smaller the radius, if it is smaller, the pressure will be high, and if it is larger, the pressure will be low. Now for this, the pressure, let's say P1, and for this the pressure is P2. So we can say that P1 is greater than P2 because it has lesser radius, and according to the excess pressure formula, the pressure P depends on inversely to the radius. So it has smaller radius, larger radius, smaller pressure. Okay. So now we can say that if it is forming a bubble of a equivalent radius are equivalent, but the film is same, so the surface tension here, that will be same. So now P net we are going to calculate. So firstly the excess pressure by 1 is 4s upon R1, and P2, because surface tension is the property of surface. Okay, and surface means specifically the interface, that thin film, that is not changing. It is not like कि soap bubble, जब दो soap bubble आपस में मिल रहे हैं तो material of soap will change. That's going to change the surface tension, but here the material is same soap के bubble हैं, they come closer, make a another soap bubble. So P2 here will be 4s upon R2. Now, equivalent, we know that P1 minus P2, P1 is greater than P2. So excess pressure, this excess pressure is the pressure of the finally formed sphere. So we can say that this P net is 4s upon R C, which is the radius of this collapse sphere जो बाद में बना. So it is nothing but PO plus 4s upon R1. You can also neglect this PO. It is the outside pressure. It is, however, it is going to cancel it out here. So this expression. Now 4s upon RC, which is the equivalent radius, is given by 1 upon RC equals to 1 upon R1 minus 1 upon R2. Got it? So RC here will become finally that this is the RC. So it will become R1 R2 by R2 minus R1. Got it? So have you got it, student of JNV Ramnagar? It is not R1 plus R2 by 2. No, it is R1 R2 by R2 minus R1. Clear है? Okay. Then we will move on. Got it. Got it. Thank you so much. So this is the expression for when two bubbles collapse and forming a new bubble. Okay. So these types of question you will also see in the your JEE mains or NEET examination. So try to apply the same formula. Okay. So they will form a new bigger soap bubble. Got it? Now try to solve this question based on the formula that I have told you. The excess pressure of one soap bubble is 4 times the other. Now find out the ratio of volume of both the soap bubbles. Try to find it out. I'm giving you 2 minutes. No, this question requires only 1 minute. So I'm giving you 1 minute to solve this question. Come on, guys, try to solve it. JNV student of JNV Baleri, Samsung Lab 2, and student of JNV Ramnagar. So try to solve this. Giving you 1 minute. Here, what is given, just I write for you. So excess pressure of one soap bubble is 4 times of the other. Let's say P1 is 4 times of the other soap bubble P2. So we can say that P1 by P2 is 4 upon 1. Okay. Now use the expression I have just told you and try to get the answer. So 30 seconds has passed. Come on, guys, you can do it. You can do it. I know. So now the 10 seconds remaining. Oh my god. So student of JNV Ramnagara has got it. It is 1 by 64 and we will see it. I'm not saying that it is correct, but you have got it, guys. Very good. So a lots of cheering for JNV Ramnagara student and others also, because I hope and I believe that they have tried it. Okay. So we will see it. So it is very simple because we know that the pressure will vary according to this expression. So P1 by P2 will be an inverse relation of R2 by R1. Okay, so R2 by R1 is 4 here. Okay, so we have to take the ratio of volume. So it is V1 by V2. We know that V is equals to 4 by 3 pi R cube. 4 by 3 pi R1 cube divided by 4 by 3 pi R2 cube. So this will cancel out. So V1 by V2, R1 by R2. Now we know the R2 by R1. So we have to reverse it. So it will be 1 by 4 cube. 1 by 4 cube is 1 by 64. Okay. So very good. Student of JNV Ramnagara, you have got it. Very good. So now the solution, we have did it right. So we don't need to look at the solution. Now the angle of contact and capillarity. This is the topic of today and also the previous topics also. So we will look at the deep end of this topic, the angle of contact and capillarity. The angle of contact is explained by the concept of adhesive and cohesive forces. Okay. So just recall the concept of adhesive and cohesive forces, then we will bang it up. Now the angle of contact, by definition, it is the angle made by the tangent that we draw. Let me tell you in our projector. So let's say this is a liquid drop and it is placed on this. So the angle of contact is the, here the contact here, this, let's say this is a liquid drop. So this liquid is making contact with air. Okay. This liquid is making contact with solid also. So angle of contact is given by, if you draw a tangent to the point of contact, remember my word and focus on my word, what I'm telling. So angle of contact is, now this is, let's say SL, we can say it, we will say this P, and if I draw a tangent to the contact point of this liquid and solid, so let's say this be the contact, this be the tangent. So it is the angle between, it is the angle between solid and liquid contact with the tangent at that particular point. Again, it is the angle between solid liquid interact point to the tangent at that point. Okay. Now we will understand it by here. So the angle between tangent to the liquid surface at the point of contact and solid surface inside is termed as the angle of contact. Same thing I have told you. This is the sphere, and let's say this is the point of contact here. Okay, so you will see it. The point of contact is not completely relaxing on the surface. So this is the tangent. I'm not drawing it to the scale. This is the tangent at the point of contact, and this is the point of contact between this liquid and solid. So it is the angle between the point of contact, the line drawn to the point of contact, and the tangent drawn to the point of contact. Okay. Now we will deal it with in a more detailed way. Why we are studying it? Okay. So it is denoted by theta. It's a, so angle of contact is different for different types of liquid and different types of surface on which it may interact. Okay, got it. Now, some of you have might have think if you have a greasy, if you apply oil on your hand and you take the water, so water will slide easily. Water will not going to wet you. And in other case, if you do not apply the oil, you take water on your hand, it will going to wet you. Now, why it is happening? It is happening because of the change of surface. Because now on your hand, it's not only your hand, it's oil also. So water is making contact with oil. Okay. So if you will tell me, it's a very interesting concept here. If this is a, let's say, particular liquid, and we have to decide whether it is making contact with it or not. Okay. And let's say this is the surface. Now, we know the adhesive force and cohesive force. Adhesive force are the forces between different molecules. So let's say we have a liquid, we have this surface molecules. So if the molecule of this surface applying a force, this is the, let's say, this is the adhesive force, and inside there is also attractive forces acting, which is nothing but the cohesive force. Now, if the cohesive forces are dominating, so the contact surface will shrink because here the cohesive forces are larger in nature. And let me use another ink. These are the cohesive forces, which is inside the liquid drop or inside the liquid, because it is acting in between the same molecules. So these are the cohesive forces. But these are the adhesive forces. Now, if cohesive forces is greater than adhesive, so they will not going to make contact with this, because in the contact point, let's say this is the surface, and at the contact point, they will try to, adhesive force try to pull it here, but cohesive force try to pull it upside. So if C is greater than A, they will pull up. So liquid is not going to make so much of the contact with the surface. So in the case of water and grease or water and oil, you can say that the interaction forces between water and oil is less than the interaction forces between water and water. That is why it is not making the contact and it is not wetting the surface. Making contact, what it means, you are wetting the surface. Okay, but if, same scenario, if this cohesive force is less than adhesive force, then this will dominate and it will make more contact with the liquid, and now the surface will look like this. Now you calculate the angle of contact. The point of contact is this, tangent will be drawn in this direction. And this is the surface inside the liquid. The angle will be theta. So here the theta is acute. And here, in this case, the theta will be obtuse. Obtuse means greater than 90 degree. Okay. So do not confuse with this term. If theta is acute, which means it is less than 90 degree. And if theta is obtuse, it means it is greater than 90 degree. Now, got it? I think you have got it. Any kind of doubt in this? If you are clear with this, just give me a thumbs up. I will move on. Okay. Okay. Very good. So I don't think that I need to explain much more of that. So it is different at the interface and of different pairs of liquid and solid. I have told you, if the cohesive forces are in dominating, then it will make the cohesive force. Cohesive के C से याद रखो. What is the shape of C? C. So cohesive dominating, which means it is not making so much contact. We will have a surface like this. Okay. And rest opposite. If the adhesive force is acting, you can say the A is will be drawn like this. So they will make contact like this. You can remember this by. Okay. Got it? For C, the shape will be like this. For A, the shape will be like this. Now, you can say here the shape is here is C, but this is the another fulfillment. Na? We have filled the liquid inside a tube. In that case, we have seen the liquid on the free surface. Okay. So, in that case, the theta is acute, which means, what does that mean? It will going to wet the surface, because if you just invert it, it will be like this, na? It will be like this. It is a shape of A, which means adhesive forces are dominating in nature. Got it? So this specific curve is nothing but it is called concave, sorry, yes, concave meniscus. Okay, two types of meniscus we have formed. Let me discuss it. This. So in this case, the angle will be obtuse. Now, so this value of theta will determine whether the liquid will spread on the surface or it will not spread on the surface, or it will form a droplet on it. So this story I have told you, if the acute angle is there, it will wet it or spread the surface. And if this is obtuse, it will not going to wet the surface. Okay. Now the capillarity. Yes. The capillarity. Capillarity have come from a term capillary. Capillary. And capillary we have derived from a term, a Latin word, which is capilla. Capilla means very, very thin. Okay. So remember this. It's a very, very thin tube that we have considered. So capillary tube is a very long tube, very long, but very small diameter. It is as thin as your hair. So these hair you can consider, one of your hair is you can consider as a capillary tube. Got it? Now, why we are seeing this capillary? Because the application of capillary that we have seen, if this is a capillary and we have put it inside a liquid, so liquid will rise up in this. Okay. Or if we change the liquid, so liquid will go down in this. So these two phenomena will happen, has happened with this capillary, and it rise up without any external force, and it is also doing work against the gravity, because gravity try to pull the object, any object, and it is rising up against the gravity. So why is this happening? We will understand it in the action of capillary action. So capillary action is the ability of liquid to flow in the narrower spaces without assisting of or even in the opposition of the external force like gravity. I have told you in the simpler word there. Okay. Now, this is the capillary. So it will rise up in the liquid. Okay. This is the water glass system. So capillary rise here. If you take the mercury, so it will go down. Okay. And the meniscus of the mercury is convex. This is the convex. If the meniscus or the, I will discuss it. What is a meniscus? Meniscus is the contact surface of the liquid, free surface of the liquid, the shape of the free surface. So there are two types of meniscus. Here you will see it is a concave mirror. You will see this in the optics chapter in your 12th class, but for now you will see it as a concave, and this is the convex. If liquid is bulging out, so it is a convex. If liquid is going down, it is a concave. Okay. So here the meniscus I have discussed. So meniscus is the curve of in the upper surface of the liquid close to the surface of the container or another object, and it is caused by the surface tension. So you will see in this example, this is slightly going down. This is because of adhesion, and this is here the cohesion force is dominating. Okay. That is why it is try to pull it together. And this, because if you take a flat surface, this is the flat surface of liquid, and if the cohesive forces aren't dominating, so liquid want to pull it from the surface, so it will form a bulge out here. It will make lesser contact with the surface. But if the adhesion force is dominating, so these walls will pull the liquid down, so the surface will look like this. Okay. Now it can be either concave or convex, depend on the liquid and the surface. Now the derivation for calculating capillary rise, the ascent formula. So I will derive it in my own. You just note it. So we have a capillary which is inside a liquid, and the liquid will rise this in this capillary up to a certain height, let's say h, and we have to calculate this height. Okay. Now I have taken water example. So meniscus will be concave. So I will draw it in a detailed view here. I will taking the bigger size so that you will understand it more. So it is the concave down of liquid. This is liquid, water. Okay. So now here the contact surface, we can say here the surface tension will apply here in this direction with the contact, and this is another contact, this. Let's say the angle here is theta. So here also this will apply in this direction. So the net resultant, we can say the surface tension will act in downward direction. Okay. This is a point, let's say O. This point is representing the radius of this capillary. So R here is the radius of capillary. Capillary. And this, let's say point P, and this has a radius capital R. This capital R is the radius of radius of meniscus, this concave meniscus, okay, which is concave. Now, if you will see here, this angle is theta. This total angle between this surface and this surface, this one and this one is 90. If this is theta, so this angle would become 90 minus theta. Okay. So again, if this is 90 minus theta, so this will become theta because this and this are perpendicular. So this will become theta. So here you will have small r, you will have capital R, and this angle is theta. So we can say that the component of r in this direction is small r. We can say that r cos theta is equals to small r. So capital R, you can say it is r upon cos theta. Now, if you will see this, this is nothing but a cavity. If there is a liquid upside and there is no liquid, let's say here, if you make it a complete system, complete sphere, so it will look like as the air bubble. Outside of it is liquid and inside is air. So we can have the formula for excess pressure. No? We have the formula for excess pressure inside the liquid. Okay. So we will consider a point here inside this. Let's say this point is B, and at outside, just outside, we have considered a point A. Okay. This. So the pressure difference will be PB minus PA, and it is nothing but the excess pressure because it will behave as a air bubble. So for air bubble, it is 2s upon the radius of the bubble. Radius we have considered capital R. Now, if you put the value of capital R here, it will become 2s over small r upon cos theta. It will go up. This will result in 2s cos of theta divided by small r. Okay, this is the excess pressure we have. Now, we know that from the pressure difference formula, if the height is h and the density of this liquid is, let's say, rho, so what is the pressure difference between PB and PA? It is rho g h. So it will become rho g h equals to 2s cos of theta divided by small r. Now, h here will become 2s cos of theta divided by rho r g. This is the formula for rise in capillary. Got it? This is formula for rise in capillary. So note it down. Okay. Now, the same thing has been done here, but it makes you feel complicated. So I have did it in a simpler way. The same formula we are going to derive here, which is 2s cos theta upon rho gl. So the same formula you can use for capillary fall also. Now, if we have an insufficient height capillary, okay, the height of the capillary is not sufficient. Let's say we know that ki liquid can rise in 10 centimeter in that capillary, but we have taken a 8 centimeter capillary. So what will happen? Will the liquid will fall outside it or not? So from the formula, you can say that height up to which the liquid can rise up will depends on the surface tension of the liquid, radius of the capillary, density of the fluid. Okay, got it? Now, These all are constant terms. So h depends entirely on the theta. Theta is also here. So if you change the angle of contact, which can only be changed by changing the liquid. Okay. So if these things are constant, so liquid will not fall out. So h depend entirely on theta. If capillary of insufficient height we have used, then the contact angle will change accordingly. But liquid does not flow out from the capillary. Okay? Because these all are constant. So theta will can only vary. So theta will adjust itself. Okay? So if this is the height, let's say height यहाँ तक पानी भर चुका है. This is the height. Now it will rise more. So it will change the meniscus of it. Okay? Up to a certain level. So liquid will not come out instantly. Okay? You can solve this example. Water rises to a height of 4.5 centimeter in capillary tube of radius small r. Find small r assuming the surface tension of the water is 72 dyne per second. You have to convert this dyne. This is the homework for you. Okay, try to solve it at your home. So water rises, height दी हुई है. This formula h is equals to 2s cos of theta divided by r rho g. So height is given to you, surface tension is given to you, angle of contact is given to you. Although the density is also given to you, gravity you know, only r you have to calculate. A very simple question. Now, if I talk about the summary, so we have done the forces of attraction between molecule of same material are known as cohesive force, and between molecules of different material is known as adhesive forces. Surface tension is the net effect of cohesive force in downward direction on any surface, and it is formulated by force per unit length. We have seen it. Surface energy is the potential energy contained by the molecule of liquid surface, due to which they stay on the surface against the inward attraction by the other molecules. And due to the properties of the surface tension, a drop or a bubble tries to contract, so compresses the matter enclosed, hence the accessing the pressure. So we have an excess pressure there. We have just seen it. Excess pressure for inside air bubble and liquid drop, it is 2s upon r. For soap bubble, it is 4s upon r. Angle of contact is the tangent of the liquid surface at the point of contact, and solid surface inside is termed as the angle of contact. We have seen it. Capillary action, we have also seen it. And the formula for capillary rise and fall is 2s cos theta upon rho g r. So by the end of this formula, I end this lecture and this chapter also. If you have any kind of query, any kind of doubt, you can ask. Otherwise, the lecture is being over for you guys. Thank you so much for being attentive. Any kind of doubt you can ask. Otherwise, the lecture is being over. Thank you so much.